Math 2414, Taylor and Maclaurin series, video 6, Taylor series for e to the x power at x equals 2. All right, so far we've kind of developed some techniques. We've gotten real theoretical at showing when or proving that a Taylor series will converge to the function it's approaching by showing that the limit of the remainder approaches 0. But for the most part, especially at this level, we're going to focus on actually building the series and finding the interval of convergence. All right, so you'll notice right here I have got the formula for a Taylor series centered at x equals a. In general, a function is equal to the sum from n equals 0 to infinity of the nth derivative evaluated at the center a over n factorial times x minus a to the nth power on some interval of the form a minus r to a plus r, where r is some positive radius of convergence. All right, so if we're going to do this, we need to concentrate on finding the derivatives because everything else is fairly straightforward. So if we can focus on what this is going to look like, then we're pretty much home free. All right, so what will the derivatives look like evaluated at a? And in this case, a is equal to 2. So we just need to figure out what our derivatives look like. But if your function is e to the x, excuse me, let's put this back to draw for a second. If your function is e to the x, it's one of the easiest functions to take as many derivatives as you want. If f of x equals e to the x, this implies that the nth derivative of x, the nth derivative of f of x is equal to e to the x for all values of n, or rather all of your whole number values, 0, 1, 2, 3, etc. Recall that the 0th derivative means the original function without taking any derivatives at all. So, excuse me. So since our center is at 2, then putting in 2 into the nth derivative, excuse me, folks, hold on, let's try that a little bit better. If we put 2 into any derivative, we're going to get e squared. Well, this implies that our series is going to be the sum of n equals 0 to infinity of e squared over n factorial, it's an exclamation mark, times x minus a, except if we're centered at 2, then a is 2, to the nth power. So at this point, we've technically found our series. We found exactly what we wanted, a function that is approximated by this series, rather a series that approximates the function that we were given. We do know that the Maclaurin series for e to the x is convergent for all values of x. Does that mean the same thing for this Taylor series? Well, we could loosely say, sure, but why don't we go ahead and check for the interval of convergence? And we can do that by doing the ratio test. So let's do the ratio test and see if we get convergence everywhere. And if not, where do we get convergence? Remember that the ratio test is the limit as n approaches infinity of the ratio of the n plus first term of the series to the nth term of the series. But since our term is essentially a fraction, I'm going to move this parentheses to the top when I take the reciprocal. But since our term is essentially a fraction, then instead of dividing by the nth term, we're going to multiply by its reciprocal. All right, so the limit as n approaches infinity of the n plus first term, so we put n plus 1 in and we get e squared times x minus 2 to the n plus 1 over n plus 1 factorial. And then to divide by the nth term, we'll multiply by its reciprocal. So that would be n factorial over e squared times x minus 2 to the nth power. All right, let's see what kind of canceling we can do. If we subtract powers from the x minus 2, then n plus 1 minus n is just 1. So everything down here is gone. And we've played this reducing of factorials of n factorial and n plus 1 factorial. But just recall that n plus 1 factorial starts out with n plus 1, and then it resumes with basically n factorial, and then n times n minus 1 all the way down times 3 times 2 times 1. In fact, what you could think or write is that n plus 1 factorial is equal to n plus 1 times n factorial. When defined recursively, that's actually the definition of how you do the next factorial by multiplying it by the next value. But if we do that, then basically everything's going to cancel except this n plus 1 in the denominator. So let's just make that a move that we do almost automatically, that this n factorial will reduce into that n plus 1 factorial to leave just an n plus 1. And let's see what that leaves us. Now we have the limit as n approaches infinity of the absolute value of, oh, I forgot to mention, the e squareds cancel. They're matching factors, one on top, one on bottom, so they're both gone. The only thing that's left on the top is the x minus 2. The only thing left on the bottom is the n plus 1. Since the x is independent of the n, the factor of x minus 2 in the numerator can be pulled out of the limit, since the limit is talking about what n is doing, not what x is doing. That leaves the absolute value of 1 over n plus 1 in the limit, but that limit will be 0, and then 0 times anything, of course, is 0. And remember, what we just found was the limit that we calculate when we perform the ratio test. And if that limit is less than 1, we get convergence. Well, this limit doesn't depend on the value of x. It's always equal to 0. So since our limit is less than 0, the series converges for all x an element of negative infinity to infinity. In other words, it converges for every real number. Now, showing that it converges to the function is an issue of doing the remainder and Taylor's theorem, but we're going to bypass that for now and just conclude that e to the x is equal to the sum n equals 0 to infinity e squared over n factorial times x minus 2 to the nth power for all, almost use a symbol I don't think I've introduced to you, for all x an element of that interval. And since it's coming to the surface, I'll go ahead and introduce it to you now because you may see it in future math classes. There is a symbol for the phrase for all. It kind of looks like an upside down capital A, but the horizontal line is a little bit longer. The symbol for the phrase for all looks like that. So if you ever see that symbol written somewhere like that, you simply read it as for all. And I think I'm going to start using the symbol more regularly because as a mathematician, it's just in my nature to write it anytime I say the phrase for all. So e to the x is equal to that series for all x in that interval. And if we wanted to expand the series just for kicks, then we could say that e to the x is approximately, well, it would help if I had the series here to look at. Here we go. There's our series, our Taylor series. So if we were to take this out to a few terms, if n equals 0, then we get e squared over 0 factorial, which is 1, times x minus 2 to the 0 power, which is also 1. So we get e squared. Plus, if n equals 1, we get e squared over 1 factorial, but 1 factorial is 1. So we get e squared times x minus 2 to the first power. If n equals 2, we get e squared over 2 factorial, which is 2, times x minus 2 to the second power. If we put in n equals 3, we get e squared over 3 factorial, which is 6, times x minus 2 to the third power. And even though I don't have room, I'm going to write one more term, plus e to the fourth over 4 excuse me. I fell into that classic trap of changing the power on the e's. The e's are all e squareds because that's what the value of the derivative was, no matter which derivative we had. But what's changing is the denominator, which is the factorial. So if it were 4 factorial, we would have 24 times x minus 2 to whatever the current power is, which is 4. And then we could go so on and so on and so on. The extra plus there is bothering me. All right, so to review, finding this Taylor series is pretty straightforward because the derivatives were the same no matter which derivative we took. That won't always be the case, as we will see in subsequent videos. Come on, let's end the video. Thank you.